Welcome to my talk. This is Jean work with Densu Onkan and Tamir Bashar. So this is the outline of the talk. I have a problem formulation, and then I look into the existence of optimal solution for two criteria, Bayesian and Neyman-Pearson, and then we'll have the conclusion. So this is the problem formulation, and we're going to look at a decentralized detection problem with a parallel configuration. And we have n peripheral sensors, and then we have a fusion center where the final decision is made, which hypothesis is true. And then we look into M hypothesis in a general problem for the Bayesian formulation, and each of these will have a prior probability that we know for the Bayesian formulation. And then each sensor will have an observation on the hypothesis. This is just the same hypothesis, but each sensor may have a different sensor space, and this observation space could be finite or infinite. And then we assume that we have this drawn distribution of the observations given each hypothesis, which we denote by P sub I, y1 to yn. Okay. So this is the configuration of the parallel structure. So each of the peripheral sensors has to make a local decision. It has to send out a local decision from 1 to capital D, and each of these is denoted by dj, where j is the sensor. And at the fusion center, doesn't have access to the whole observation on the hypothesis, but instead it receives all the messages from the sensors, and then it makes the final decision. So the reason that we have this decentralized configuration is that first of all, we want to enhance the reliability of the final decision, and then each of these sensors could send the whole observation to a fusion center if there's no communication constraint. In that case, at the fusion center, we just implement a regular hypothesis testing problem for one sensor, but then due to communication constraint, each of these sensors just can send something like a local decision from a finite alphabet, or you can also think of that as a quantized version of the observation to the fusion center. But at the fusion center, we have to make the final decision of which hypothesis is true. Yeah, so that's the configuration. And then, like I said, each sensor has a decision rule, which is a mapping from the observation, its own observation space to one of these alphabet from 0 to d-1. And then at the fusion center, the fusion rule is something that maps all the messages it receives from the sensors to one of these hypotheses. So in the Bayesian approach, we look at a joint optimization of the rules at the peripheral sensors and the fusion rule to minimize the probability of error. This is not a general formulation. For a general cost structure, we have something like called Bayesian risk, but if we pick a uniform cost structure, then we have the probability of error. and it's not much. There's not much difference. So just for simplicity, we use the probability of error here. And then in Neyman-Pearson approach, we try to maximize the detection probability, given an upper bound on the false alarm probability at the fusion center. This is just standard hypothesis testing. So I want to bring up something that we call a general rule and threshold rule, because normally in a one sensor problem, what we normally see is the threshold rule on the likelihood ratio, but it's not. In general, it's not the case for the decentralized detection problem. So the general rule is just a rule where we partition the observation space into M regions, and if the observation falls into one of those, we pick the corresponding hypothesis. This is the general rule, and then we have the threshold rule, which is something we normally see in one sensor problems, where we look into the likelihood ratio test, and we have a threshold. This is just for a binary hypothesis testing problem. But again, in this problem, we look into the joint optimization of the whole system to find in the Bayesian approach, we minimize the probability of error, or in the Neyman-Pearson, we maximize the detection probability given upper bound on the false alarm probability. But if we look into the this, then regardless of the rules at the peripheral sensors, we look into the fusion center, and we'll see that all the messages from the peripheral sensors are actually can be considered as observations of the fusion center. And what the fusion center faces at here is just a one sensor problem, and even like for both Bayesian approach and for Neyman-Pearson approach. So put it in another way, that is if all the optimization rules at the peripheral sensors have been optimized, then this one will be the fusion rule at the fusion center will just be the regular rule that we see in a one sensor problem. So this is just at the fusion rule. We normally for Bayesian, we have the rule will be something like this. This is just the rule for a one sensor problem, and then we look again D1 to Dn, which are the messages from the sensors. Now actually the observation of the fusion center, and we have the threshold rule here for the fusion center, and then with that rule we have the formulation of the probability of error at the fusion center like this, and also for the whole system. This is familiar, but then we look into this. We just this is actually pi 0 and pi 1 are the prior probabilities of hypothesis 1 are 0 and H1 and H0 and H1, and then we look into this. We just see this conditional probability is the summation of this probability of the conditional probability of this where with all the combination of this where the likelihood ratio is larger than threshold, larger or equal to threshold, and similarly. So we're going to use this in the later argument for the existence of the optimal solution. So this is from Stiglitz, and he actually proves the existence of optimal solution for this parallel configuration, given that all the observations of the sensors are conditionally independent, given each hypothesis. It's just some notation, and this we denote this to be the probability, the conditional probability given Hi, that the sensor J, say D, this is a peripheral sensor, the probability that it sends out a D, And then we group all of these together for each hypothesis. This is probability that it sends out 0, probability that it sends out d minus 1. And this sum, all of this sum to 0, the sum to 1. And then we again group all these all these vectors with different hypotheses into one. And this is it. And again, for notational simplicity, we define something like this. This is a distribution of all the sensor matrices given all hypotheses. And statistically proves that the set of all these Q given and then that resulted by all the deterministic decision rule at peripheral sensors is a compact set. And then if you look at the again, like I said, if we look at the formulation of the probability of error here, it's just a linear function on this probability. So by Weierstrass theorem, we have the existence of a solution given that with the assumption, with the conditional independent assumption of sensor observation. So what we are trying to do in this talk is to extend this argument to the case where sensor observations are not necessarily conditionally independent. So we have proved that this is something intuitive, but we have proved that even with a very simple decentralized configuration, the probability of error cannot be expressed solely as a function of the marginal distributions. So this is intuitive. So that's why we cannot use the previous argument for the case of conditionally dependent. So the natural extension is now, instead of looking at the marginal distribution of the sensor matrices, we look at the joint distribution. So we again some notation. We look at all the decision rules at peripheral sensors and use this big capital gamma to denote the Cartesian, product set of all the decision rules at all the peripheral sensors. And we look into this instead of look at the marginal thing. We look into the joint distribution. Given each hypothesis, we look into the probability that sensor 1 says D1, sensor 2 say D2, and sensor this is an abuse of notation actually. If that sensor 1 says something and then each sensor says this is the probability of this. And again, we group all of this kind of thing into a big vector. First, we group this big S gamma given Hi is everything given hypothesis Hi, and then this is for all hypotheses. So basically, this is similar to previous definitions, which the exception with the only difference is that we now look into the joint distribution of sensor observation. Yes.
Are there only finitely many policies? I mean, all alphabets are discrete.
Yeah, the fusion center is finite. Number of fusion centers is finite.
Yeah, but how about the observations? Are they discrete also?
They could be discrete. The observation of a peripheral sensor could be discrete or continuous. Doesn't matter. Yeah. But later on, we use integration, but it could be discrete as well, because in network security we look at like number of bytes or duration. It could be discrete. Like for example, we look at number of bytes. We look at duration of a connection. All the parameters of a connection, and we try to see if it's a normal connection or some kind of.
But if it was discrete, there'd only be finitely many policies, and then one of them would have to be optimal.
Yeah. If it's finite, yeah, that's right. Yeah, so again, we see even in this case, P is probability of error. The Bayesian risk is a continuous function on this, and for the same for a fixed fusion rule. And I think that just the most difficult part of this is just to prove the this set that resulted from all the decision rules at peripheral sensors, and now we're just talking about deterministic decision rules here. We have to prove that this set is compact, and if this set is compact, then again by Weierstrass theorem we have an optimal solution. So we have this theorem. This is again deterministic decision rule at peripheral sensors, but the set that resulted from this is basically joint distribution of all the sensor observations. This set is compact. 3 minutes. So this is an outline of the proof, and we basically use a mapping, and then we try to prove this is continuous, and then this F is compact, and then S is compact. So this is the result. If the Bayesian criterion is used, then there exists an optimal solution, where peripheral sensor is deterministic general rules, and the fusion center is deterministic threshold rules. So, and remember that for the case of conditional independent assumption in cyclics, the peripheral sensors actually we have a stronger result that peripheral sensors actually use threshold rules as well. But for the without that assumption, it no longer holds, and we also cyclic gives a counterexample of a case where the threshold rules are actually not optimal at the peripheral sensors. So for Bayesian, for Neyman-Pearson, we actually use a randomized decision rules at the peripheral sensors, and we end up with something that is a convex hull of the previous set, an S bar that is a convex hull. And if you look into the Neyman-Pearson, it includes a randomization at here. This is at the fusion center. So we end up having this false alarm probability, and the detection probability again is a continuous function on the S bar, which is the convex hull of S. And then again, we for a fixed fusion rule, we have an optimal solution, and it's also like it makes sense only in the continuous case, like as it said. But then we have again we have a finite number of fusion rule here, because this is basically just finite number of there's n messages here at the fusion center. This is just the way you break these all the combinations of B1 to Bn into 3 subsets. With one subset, the probability, you say one subset you say 0, and with the third subset you randomize on the decision. So again, there's a finite number of fusion rules at the fusion center. So with the same argument, we can say that there exists an optimal solution for the Neyman-Pearson criterion as well. And this is the result. This is how we compute the joint distribution of sensor messages given the joint distribution of observations. This is for the continuous case. Yeah. So to sum up, we showed that the previous argument for conditionally independent assumption cannot be extended to the general case where sensor observations are conditionally dependent. And then we look into the Bayesian formulation and Neyman-Pearson problem, and we show that there exists an optimal solution for those criteria.
Thank you very much.
Yes.
Is it obvious that for the Bayesian problem you don't need to consider
the randomized quantizers?
No, no, for Bayesian we don't do randomization. Just
so is it? Can you show that it's optimal not to consider? It's optimal to use deterministic quantizers?
yeah, I'll show that. Yeah. If no other, thank you. Okay.